Hello friends, we start a class on real sequence. This is our 8th class. In previous class we discussed some theorems on bounded sequence and divergent sequences. In this class we discuss some results on limits of a sequence and use the results we solve some examples. Okay, so we discuss some results and some examples. Okay, so let us start. Theorem. Okay, 1. If xn and yn be two real sequence, okay, real sequence, okay, if xn and yn be two real sequence and the sequence xn converges to x and the sequence yn converges to y. Clear? Then number one, the sequence xn plus yn. The sequence xn plus yn. What is the sequence? The sequence is x1 plus y1, this is first term, x2 plus y2 is second term, x3 plus y3 is third term, xn plus yn, this is nth term, and so on. Okay, so if xn and yn be two real sequence, then this is also a real sequence, xn plus yn. Okay, this is a real sequence and the sequence is this. Okay, if xn converges to x and yn converges to y, then xn plus yn, the sequence converges to x plus y. Okay, this sequence converges to x plus y, that is x means limit n tends to infinity xn plus y means limit n tends to infinity yn. Okay, so if xn converges to x and yn converges to y, then xn plus yn converges to x plus y, that is the limit can be distributed in sum. Okay, clear? Similarly if c be any real number, then the sequence cxn, this is also sequence, this sequence is cx1, cx2, cx3, cxn, so on. Okay, this is the sequence, and this sequence converges to cx. Okay, if xn converges to x, then and c be any real number, fixed real number. Okay, this is a fixed real number. Okay, this is a fixed real number, then this is a sequence and this sequence converges to cx, where xn converges to x, that is c into limit n tends to infinity xn. Okay, so limit can be distributed in scalar multiplication. Okay, so 3, the sequence xn yn, this is x1 y1, x2 y2, x3 y3, and xn yn. Okay, this is the sequence. This sequence is also convergent, and if xn converges to x or yn converges to y, then this sequence is convergent and converges to this is also convergent and converges to xy. Okay, that is limit n tends to infinity xn into limit n tends to infinity yn. Okay. Also xn by yn, this sequence x1 by y1, x2 by y2, xn by yn, so on. This sequence is also convergent provided is convergent provided yn not equal to 0 for all n belongs to n and y not equal to 0. Okay, that is each term of yn are non-zero. That is yn be a sequence, yn be a real sequence such that no term is 0. Okay, every term is non-zero. Okay, for such yn and the limit not be 0 and such a limit y. So here the condition is yn not equal to 0 for all n and y not equal to 0. Okay, it is the limit of yn not equal to 0 and converges to x by y, that is limit xn by limit yn. Okay, clear? This sequence, if xn converges to x and yn converges to y, then xn by yn is converges to x by y, provided each yn not equal to 0 and y not equal to 0. Okay. Next 5. If xn greater than equal to 0 or maybe greater than 0, okay, anyone. If xn greater than equal to 0 or maybe greater than 0 for all n, then the limit of xn, that is x, limit n tends to infinity xn, that is x, is also greater than equal to 0. Okay, if each term is non-negative, if each term is non-negative of a sequence, then the limit is also non-negative. Okay, for positive it also be true, because if xn equal to 1 by n, this is greater than 0 for all n, but xn tends to 0 as n tends to infinity. Okay, this is our example as for this case. Okay, so if each term of a sequence is non-negative or positive, maybe positive, for all n, then this limit must be greater than equal to 0. Okay, similarly this result is also true for less than equal to. Okay, this result is also true for less than equal to. Now use the above result if xn greater than yn for all n belongs to n. Okay, if xn greater than yn for all n belongs to n, then limit xn is greater than limit yn. Okay, greater than equal to, sorry. Okay, here the equality may be occur because if xn equal to 0 for all n and yn equal to 1 by n for all n, then xn tends to 0 and yn also tends to 0. Okay, clear? So the equality So sorry, this is yn, this is xn. Okay, then xn is greater than yn for all n. Xn is greater than yn. So if yn is 0 for all n and xn is 1 by n for all n, then xn greater than yn for all n. So xn, but xn tends to 0 and also yn also tends to 0. So the limit is equal. So for strictly greater than, the equality may be occur. So if xn greater than yn for all n, then limit xn is greater than equal to limit yn for n tends to infinity. Okay, that is x is greater than equal to y. Clear? Okay. Now another result. Now another result. 6, 7. Okay. If un be a real sequence, and limit un equal to 0, if un be a real sequence and limit un equal to 0, if and vn be a bounded sequence. Okay, bounded sequence in R. Okay, un be a real sequence and limit un equal to 0 and vn be a bounded sequence in R. Okay, then limit n tends to infinity un vn, this is equal to 0. Clear? If un converges to 0 and vn be a bounded sequence, then the sequence un vn converges to 0. Okay, but the converse may not be true. But the converse may not be true. Okay, so I only prove this. Okay, I only prove the 7. Okay, so since vn is bounded, so in previous classes we discussed the definition of a bounded sequence. Okay, so vn is bounded, so vn is bounded. Okay, this implies there exists m greater than 0 such that mod of vn is less than m, less than or less than equal to for all n belongs to natural number. Okay, there exists a positive number m such that mod of vn is less than equal to m for all n belongs to natural number. Okay, now limit un equal to 0, so this implies by the definition of a limit of a sequence, for each epsilon greater than 0 there exists natural number k belongs to m such that mod of un minus 0 is less than epsilon. Okay, for all n greater than equal to k. Okay, here epsilon is arbitrary, so we can choose an epsilon, so we can take epsilon by 2, epsilon by 3, and in my choice. Okay, so we take epsilon by m. Okay, this is a real number because m is non-zero, so m is non-zero, so epsilon by m is a real number. Okay, clear? So this is 1 and this is 2. Clear? Now we have to prove that limit un vn equal to 0. So mod of un vn minus 0 is less than epsilon. We have to prove that. So mod of un vn minus 0. Okay, if this is less than epsilon, then we can say limit un vn equal to 0. So un vn minus 0, this is equal to mod of un vn is equal to mod un to mod vn. Okay, since mod un, this implies mod un is less than epsilon by m for all n greater than equal to k. Okay, so this is less than mod even, this is less than epsilon by m for all n greater than equal to k. Okay, and mod vn is less than equal to m. So this is less than and this is less than equal to, so ultimately less than, okay, m. So cancel out m, this is less than epsilon, therefore mod of un vn minus 0 is less than epsilon for all n greater than equal to k. So by the definition of a limit of a sequence, this sequence un vn converges to 0. Okay, this sequence converges to 0. Clear? Now see the definition of a limit of a sequence. Let xn be a sequence in R and L belongs to R, then L is said to be a limit of the sequence xn if for each epsilon greater than 0 there exists a natural number k belongs to n such that mod of xn minus L is less than epsilon for all n greater than equal to k. And we write limit xn equal to L as n tends to infinity. Okay, so we prove mod of un vn minus 0 less than epsilon for all n greater than equal to k. So the sequence converges to 0. Clear? So the sequence converges to 0. Limit un vn equal to 0. Clear? But the converse may not be true. So we can take the example. Un equal to 1 by n square and vn equal to n. Okay. Clear? For all n belongs to real numbers. Then un tends to 0 and vn is unbounded. Okay, but un vn equal to 1 by n square into n, that is 1 by n, this is converges to 0 as n tends to infinity. That is un vn converges to 0 but vn is not bounded. Okay, so if un converges to 0 and vn is bounded, then un vn must converges to 0. Okay, but un converges to 0 and even vn converges to 0, then vn may not be bounded. Okay, so this is the proof of this result. Okay, now we give some examples of the results. Okay, clear? Now we discuss how we find the limit to use the above results. Okay, let us start. Example 1. Now we take the sequence xn equal to 5 plus 5n by n square. Okay, n belongs to natural number. Okay, now we find the limit of this sequence. Okay, so we find the limit n tends to infinity xn. So limit n tends to infinity 5 plus 5n by n square. Okay, so this equal to limit n tends to infinity. We can take common 5, then 1 plus n by n square. Okay, so limit n tends to infinity 5 into 1 by n square plus 1 by n. Okay, there. So if we take un equal to 1 by n square and vn equal to 1 by n, then un converges to 0 and vn also converges to 0. Then un plus vn, this is converges to 0 plus 0, that is 0 as n tends to infinity. Okay, so this is un, this is vn, so un plus vn converges to 0, and is this result. So first, by this result we find un plus vn converges to 0, and by these results we can take c before the limit. Okay, so by the results 2, okay, by the above results 2, by results 2, okay, by results 2 we can take 5 here, so we can write limit n tends to infinity xn equal to 5 limit 1 by n square plus 1 by n. Okay, clear? This is equal to 5 limit n tends to infinity. This is un, this is vn, un plus vn. Okay, so un vn converges to 0. Okay, so 5 into 0, that is 0. So limit xn equal to 0. Clear? So this limit converges to 0. Clear? Here we use these two results. Here we use this and this, this and this. Okay. Now another example. Example 2. Okay. This sequence 5 by 2n plus half whole to the power n. Okay, half whole to the power n. We have to find limit n tends to infinity xn, that is limit n tends to infinity 5 by 2n plus half whole to the power n. Okay, so we can take this is un, this is vn. Okay, so un equal to, we take un equal to 5 by 2n and vn equal to half whole to the power n. Okay, half whole to the power n. Clear? So this sequence converges to 0 because this is 5 by 2 into 1 by n. So limit un n tends to infinity equal to 5 by 2 limit n tends to infinity into 1 by n. Okay, because of result 2. Okay, so this is 0. 5 by 2 into this limit will be 0, n tends to infinity 1 by n tends to 0, so this is 0. So limit un equal to 0 and limit vn, limit n tends to infinity vn equal to limit n tends to infinity half whole to the power n. Okay, clear? So this is also 0 because in previous class we have a result, limit n tends to infinity x to the power n equal to 0 for all x satisfying mod x less than 1. Okay, for such x such that mod of x less than 1, limit x to the power n equal to 0. So here x equal to half, here x equal to half, here x equal to half, so which is and mod of half is less than 1. So the sequence n tends to infinity half to the power n is converges to 0. Okay, we use the result, we use this result. Clear? So vn also converges to 0. So this is limit un plus vn, therefore limit n tends to infinity xn equal to 0 plus 0. This is converges to 0, this also converges to 0. So 0 plus 0, that is 0. So the limit converges to 0. Clear? Okay. Now another example. Example 3. Okay. Third example is n equal to 8 by 3n whole to the power 1 by n. Okay, n belongs to natural number. This find the limit. So we have to find limit n tends to infinity xn. Okay, that is limit n tends to infinity 8 by 3n whole to the power 1 by n. Okay, so this equal to limit n tends to infinity 8 by 3 whole to the power 1 by n into 1 by n to the power 1 by n. Okay, 1 by n to the power 1 by n. Clear? Okay, 8 by 3 whole to the power 1 by n and 1 by n to the power 1 by n. So now we have some results. This limit n tends to infinity n to the power 1 by n equal to 1. So this converges to 1. So if we take un equal to 8 by 3 whole to the power 1 by n and un equal to n to the power 1 by n, then limit n tends to infinity un equal to 1. Okay, by this theorem we discussed this in previous classes. Okay, is equal to 1. Clear? And we have a result. This is a new result. Okay, this is a new result. If limit n tends to infinity xn equal to L, if xn converges to L and a is greater than 0, then limit n tends to infinity a to the power xn equal to a to the power L. Okay, that is a to the power limit xn. Okay, this is our result. Okay, this will be discussed in one of the next classes. Okay, now we just state this result. If xn converges to L and a greater than 0, then limit n tends to infinity a to the power xn equal to a to the power L, that is a to the power limit xn, that is the limit is work on only xn. Okay, so use this result, limit n tends to infinity un equal to limit n tends to infinity 8 by 3 whole to the power 1 by n. Okay, so here a equal to 8 by 3, which is greater than 0. So this equal to limit 8 by 3 limit n tends to infinity 1 by n. Okay, limit n tends to infinity 1 by n. So this is 8 by 3, this is 0. Limit n tends to infinity 1 by n, limit n tends to infinity 1 by n equal to 0. So this is 0, so this is 1. Okay, so limit un equal to 1, also limit vn equal to limit vn equal to 1. Okay, this is vn. So limit vn equal to 1 and limit un equal to also 1. Now what is our limit xn? Limit n tends to infinity xn equal to this, that is limit n tends to infinity un by vn. Okay, limit n tends to infinity un by vn. Okay, so this is converges to limit un by limit vn if each vn not equal to 0 and the limit of vn not equal to 0. Okay, that is this theorem. This we use this theorem. If xn converges to x and yn converges to y, then xn by yn this converges to x by y, provided each yn not equal to 0 and y not equal to 0. Okay, so here limit un equal to 1, limit vn equal to 1, and limit vn equal to 1, and this is not equal to 0. So limit un by vn equal to limit un by limit vn. Okay, so this equal to 1 by 1, that is 1. Okay, so limit xn equal to 1. Clear? Okay, now next example, example 4. Okay, next example 4. Our example 4 is xn equal to minus 1 whole to the power n by n. Okay, minus 1 whole to the power n by n. Okay, you have to find limit n tends to infinity xn, limit n tends to infinity minus 1 to the power n into 1 by n. You can write this. Okay, so we can take un equal to minus 1 un equal to 1 by n and vn equal to minus 1 to the power n. Okay, minus 1 whole to the power n, and this is a bounded sequence. This is a bounded sequence. And un converges to 0 as n tends to infinity. Okay, so un be a real sequence converges to 0, and vn is a bounded sequence, and this is un vn. Okay, so by this result, un be a real sequence and limit un equal to 0 and vn be a bounded sequence in R, then the limit must be 0. Clear? So here un is a real sequence converges to 0 and vn is a bounded sequence, so un vn converges to 0, so limit un vn equal to 0. Clear? Therefore limit xn equal to 0. Okay, clear? So these are some examples of limit of a sequence. Okay, now another theorem. If xn converges to L, okay, if xn be sequence which converges to L, then the sequence mod xn converges to mod L. Okay, then the sequence mod of xn converges to mod L, but the converse may not be true. Okay, proof. Okay, if xn be a sequence which converges to L, that is limit xn equal to L, then the sequence mod xn converges to mod L. Okay, so xn converges to L, that is limit n tends to infinity xn equal to L, then by definition, this implies by definition for h epsilon greater than 0 there exists number k belongs to n such that mod of xn minus al is less than epsilon for all n greater than or equal to k. Okay, so now we have to prove mod xn minus mod l. Okay, mod xn minus mod l. So this is, if this is less than epsilon for all n greater than or equal to some k, we say that mod of xn converges to mod l. Okay, so we start mod of xn minus mod l whole mod. So this is less than or equal to mod of xn minus l. Okay, because we have the result mod of mod a minus mod b is less than or equal to mod of a minus b. Okay, this is the result. Mod of mod a minus mod b is less than or equal to mod of a minus b. Okay, so mod of mod x minus mod xn minus mod l is less than or equal to mod of xn minus l, and mod of xn minus l, this is less than epsilon for all n greater than or equal to k. Clear? So therefore limit n tends to infinity mod xn equal to mod l. Clear? That is this mod xn converges to mod l. Clear? Now discuss the converse may not be true. So if we take the sequence xn equal to minus 1 whole to the power n. Okay, so this is a sequence which is a real sequence, and it is a divergent sequence. Okay, it is a divergent sequence. Clear? We discussed divergent sequence in previous class. This is a divergent sequence, but mod of xn is equal to minus 1 whole to the power n, that mod. Okay, so this is 1 for every n, this is 1. Okay, so the sequence mod xn is 1 1 1 1 and so on. So this is tends to 1, that is convergent as n tends to infinity. That is, xn is not convergent. Divergent sequence xn is not convergent, but mod xn is convergent. Okay, that is mod xn is converges, but xn is not convergent. So the converse may not be true. This is an example. This is an example to prove the converse may not be true. Clear? Okay, that's it. Thank you.